Here's our live stream. Everything is good. We share this slide deck. So today our goal is to quickly finish the context switch lecture and then start on file systems. Let me quickly remind you. Let me mute everyone. If I suddenly someone's unmute. Do this. Oh, sure. Done. Feel free to ask me any questions anytime, either on Zoom or like in chat, or just unmute and ask. So just a quick reminder. So what we're doing today is the following. We try to understand how operating system switches from one process to another, right? And there's a couple of, there is a ton of low-level details, but there is just a couple of interesting small details which are critical, right? So at the very heart of this switch function, there's one simple function, which is called switch. And this function takes two arguments. It, roughly speaking, and I'll talk conceptually, not how x86 does it, but like what conceptually should be there, and then how x86 actually implements it. It kind of has a pointer to from, which is a currently running process. We can all call it old, and a to, or a new process which we're switching to. And despite the fact that x86 implements this from in a specific manner as a context, in practice, it just has to be a data structure, which, again, we can call a context. And this data structure contains a small number of registers. And we talked about it last time. The call saved registers, right? Because when you enter switch, the only state, remember, we were packing like everything in boxes, and the only state which is unsaved yet are the call saved registers. You can say, okay, like that's only 4 on x86 32-bit machine, right? And arguably, you can also say that 2 other things need to be saved. It's the position on the stack and instruction pointer. So these 2 registers, despite the fact that they are not roughly, I don't really know how they, if you read a strict categorization of what is call saved, what is caller saved, I don't know. Maybe people say that these are call saved, but I would prefer them to be like mentioned explicitly, right? Because all these call saved registers are explicit, general registers, which machine is using, your code is using, and these 2, instruction pointer and a stack pointer, they kind of like always used by the compiler. You never really see them, right? But if you remember these 2 things that we have to save call saved registers, instruction pointer, stack pointer, into some data structure, which this function takes, then we can come back to this execution of this program later, right? Because like when someone code switch, right? So when some other function like foobar invoked switch, the return address, this label A, which is right after foobar, is saved on a stack of whatever the current stack is, right? So your stack pointer will be pointing here, and your A value will get here, right? So if you have the stack, you have the stack, you have the return address, right? So meaning that if you have this context data structure, if this one contains the ESP pointer, which points to this stack like this, for example, and has the instruction pointer, well, that's fine. So roughly speaking, you don't even like this instruction pointer will be equal to this A, right? So roughly speaking, maybe you don't even have to save it in most cases. Like, again, I don't want you to get confused, but when you build the context switch, you don't really always have to come back to this A point. There might be some other point. Maybe you will pick a point which is right before exiting to the user level. If you don't have to do anything in a kernel, you just simply say, look, I will pick this instruction pointer to point to the place in the kernel right before the kernel exits into user level, right? So we've done it in other operating systems, so it doesn't always have to be, right? But in most normal cases, the stack pointer can point to the stack. All the other registers will be already saved on the stack, all the caller registers, right? Everything else, or like previous invocation, some return function, return to like whatever trap function, some other registers were saved here, maybe return to whatever. We never really like it all jumps, so we don't have anything. So, but like return to user, so some user headers will be saved here as well, right? And so conceptually, this switch function takes a pointer to the context from which you're switching, and you only save these 4 registers into this context, and a context to which you're switching, right? So essentially, it's kind of like 2 identical data structures. There will be a context here as well. And you say, look, we know what it is. It again says it has Coley saved registers, has stack pointer, and in most normal cases, the stack pointer will contain some kind of return address here, let's say C, for example, because if it can happen that, in one case, foobar calls switch, and in another case, some other function like buzz calls switch, because switch can be called from multiple spots, like from a timer interrupt, like some explicit sleep system call, stuff like that, right? So there are multiple paths, right? And that's it. So essentially your switch function essentially says, okay, I get it. So I save, it just strictly has 3 parts. Save Coley saved registers of a process you're switching from, then switch the stack. If you have to save the stack, the old stack, you save old stack here. You switch to the new stack, and after that you restore the Coley saved registers from the context you get as an argument. Does this make sense conceptually? That's essentially what we were talking about last time. I'm just coming back to kind of review what was happening, because there were many details, but in the end, everything just boils down to this simple idea. Everyone is good? Okay, let's then go over this switch sequence one more time, right? One trick which x86 is doing is that x86 essentially places this context at the top of the stack. So right here, it's not strictly necessary, and maybe even newer versions of x86 don't do this. I didn't check, most likely they don't. But essentially this context is just on top of the stack on which you were running. It's fine. This context can be alternatively a part of the process data structure. Like in x86, the context is just a pointer to the field, which is the context field of a process data structure is a pointer to this stack, right? Let's take a look again how it works. So again, one more time. So we're running in user level, kind of on this slide. A timer interrupt, which is vector 32, preempts us, places us in a kernel. We start executing this vector 32 here. The code of this vector 32 pushes the dummy error code in a interrupt vector 32 on the stack, jumps to all traps. Your stack looks like that. That's the kernel stack, right? The pointer to the user stack is already saved here. So this pointer points to the stack of the user. the stack of the process at user level, right? So this is like, if we draw this diagram, this is like privilege level 3, and this is privilege level 0. This instruction pointer points to somewhere where the user was executing some instructions, right? Then all traps start saving all unsaved registers, like segment registers here, all user general registers with this push all instruction. It then switches the segments, making sure that the kernel running with correct privileges in DS, ES, FS, and GS segments. Then pushes the arguments to all trap on the stack. It's a trap frame which is formed on the stack. Calls the trap function. At this point, we can switch to C because we don't have to carefully control how registers and everything gets saved on the stack. We don't care anymore. So we switch to a C function. C function like handles the interrupt by using this field trap number, which points to we pushed 32 as part of the timer interrupt. Eventually get to this yield function. Yield function is getting ready to pass control to a different thread. So calls the scat function. Scat essentially, anything can happen before, right? But the core of the context switch is the switch function. It takes two arguments, as I was saying. Roughly speaking, it's a pointer to a context of a process from which we're switching. And we're switching to in x86, we're not directly switching to a process, we're switching to a scheduler. So this is our 2. Like in x86, process always switches to the scheduler. Scheduler picks the next process, switches into it, P2. Later on, P2 switches back to the scheduler. Scheduler switches back to, like, let's say P1 again, because maybe we only have 2 processes in the system and so on, right? So, but the key point is that this is from, and this is to, and nothing else is happening. And at this point, everything is saved besides the callly saved registers, right? And that's what happens inside the switch function, as I was just explaining. So the switch function, like, it says, okay, I understand everything. I have 2 arguments on a stack. Everything was saved here already. This return address of the function which called scat is saved on a stack as well, which simplifies the job of this switch function. It doesn't have to save instruction pointer. But what it does is the following. It says, okay, look, I will save 4 callly saved registers. I will switch the stacks. Remember, I said that this is like, there are 3 parts. Part number 1, save callly saved registers. Part number 2, switch the stacks. Part number 3, restore, load new callly saved registers, right? And essentially, the simplification which is made, that the context is allocated on the stack itself. So it simply pushes on the stack, saving this value on a stack. However, the layout of the stack at this point matches the definition of this context data structure. And in order to remember where this context is, what happens is that we get a pointer to a pointer. So this is the proc context pointer. And we get a pointer to this one. So we take an address of this pointer. And essentially, we're saying the current value of the stack into this address, right? So if this field, the ampersand proc context, is just a 4-byte field, right? And EAX contains the address of this field. And so we just put the value of ESP into that field, which means that now we, inside the process, so this field itself is part of the process data structure, proc, right? So because proc has a field context, we pass the address of this field and we just write the value of ESP into this field, right? And what happens at this point is that we establish this pointer. So this is the field context inside the process data structure. It points to the current value of the stack pointer. And the return address, EAP, is already saved when we call the switch function. Scat called the switch, and these 4 callly saved registers, we just save them explicitly by pushing on a stack. Make sense? Let me stop here for questions. 3 is good. And finally, the second argument, which we got here we passed it, calling convention, we pass the arguments on a stack, we save it here in the EDX register. This EDX register contains the pointer to the stack of the process, or in our case of the scheduler we're switching to. The context itself is sitting on top of some stack. That's the assumption in x86. So we just load this EDX into the ESP register, establishing the pointer to the stack, right? And the return value, return address, return C, this is where like some other part of the x86 called this switch function, save this return value on the stack while calling it. And so everything the execution will essentially continue from this return address, and whatever was calling switch before will return and will continue essentially working forward from here. Make sense? So what happens at this point is that if the stack pointer was pointing to the top of the from stack, now it will be pointing to the top of the to stack, and we will start restoring those call saved registers from this context. And as we were saying, since in x86 we're switching from a process into a scheduler, this is a stack, kernel stack of a boot process on which the scheduler is running. So let me remind you real quick how we got to this stack. So remember when we were booting into the main function, before entering main, we created a kernel stack, and we did all of this initialization, entered np main function, essentially main called np main called the scheduler, and the scheduler is the function which is running on this stack. The scheduler function never exits, so it's essentially an infinite loop. What it does here, it says, okay, I have a table of processes in a system. x86 supports nproc number of processes. So it's essentially like, instead of maintaining a linked list, it's just simply an array of processes, and they have a state. If the state is not runnable, we'll skip go to the next one. If we find, like, essentially we were running process, let's say P1, if this one was P0, maybe P2 is not runnable, the code advances forward, maybe P3 is not even allocated, then we find P4 in the running state, we say, look, it will be the next process to run. We switch the address spaces in this function, switch user virtual memory, set the state of this new process to running, and invoke the switch function, which switches essentially. We switch from process P1 into the scheduler function. Pick process, let's say in our example P4, and where in this function, this is proc is pointing to P4, we're switching to P4. And P4 will start running, potentially exit into user level, will run for a while. At some point, the timer interrupt will come back. We'll force the P4 back into the kernel. P4 gets back into the kernel and essentially does a switch function, as we were talking. And the switch function will come back exactly to this line, right? Because we called switch to this address A, got saved on the stack of the scheduler. Later on, we're coming back to the switch kernel virtual memory function, and we continue running this loop, right, in the scheduler. Let me stop again for questions. Does it make sense?
So when we context switch, we're basically going to the switch KVM part of scheduler.
Mm-hmm. Not exactly sure. What are you trying to ask here? So we're going, like, when we switch away, we're entering the switch function, right? Like the one which we're discussing. Our from is the context of the scheduler. So we have a CPU data structure which has a field which maintains the pointer to the current scheduler, the context of the scheduler on this CPU. And we have a to field. So we're switching to this process, right? And switch we just looked at switch. Switch does just one thing. It saves call saved registers, switches the stacks from to two, and then essentially start restoring from this two stack, restoring the call saved registers, right? And then this other process runs for a while and then comes back and this like returns to this A label switch KVM function, right? And this switch KVM executes, and then this executes, then we go to the next iteration of the loop, right? So there's like two loops, nested loop. One is infinite loop, and this loop goes through this all processes and the array, reaches the end of the array, starts again from the beginning of the array. And we do that over and over and over. And this scheduling policy is called round robin, because xv6 just picks processes in order, which whoever is ready to run runs for until the next timer interrupt or until the process yields the CPU voluntarily. Make sense? Does this answer your question? You
Yeah,
ask?
I think so.
Yeah. Well, we can put any logic here, right? So here we're switching to the, roughly speaking, what we're doing, and I will talk about those functions a little later, maybe. Here we're switching to the address space, a page table of a process we're switching to. Here we're switching back to the page table, which we created as part of the main function. Let me show you where we created it here in this function, kv malloc. Why are we doing this? Because the process which we were running before might exit, right? And we might have to deallocate this address space. That's why we're switching back to the kernel address space. So it doesn't always have to be this way, but it's one way to structure it, to make sure that you always have an address space, even if you don't have any more processes in the systems, like this table is completely empty, everything is unallocated. The xv6 will still keep running this scheduler loop forever, right? It will never get any new processes, right? Because everything exited, but it will continue running it. Any other questions? Good. Okay, so now we got this. We understand how the scheduler function works. So just a couple of details here. So in xv6, and we haven't talked about it yet, but xv6 supports multiple CPUs. So right now we just booted on one physical CPU 0. Remember when I was talking about the boot in the boot lecture, I was saying that according to the CPU numbers, one is chosen as the bootstrap CPU, and everything else is essentially becomes application level CPUs. We will come back to how those CPUs are woken up, but essentially this is called bootstrap, and these are application AP CPUs. And this boot will send specific interrupts to wake them up. We'll talk about it probably in about a week or two. But for each of these CPUs, xv6 maintain a struct CPU data structure. So xv6 just says, okay, I have an array. I support n CPUs. That's the maximum number. For each CPU, I have some CPU specific fields, which I like have to keep track of. And one of those fields is this pointer to the scheduler. So on each of these CPUs, CPU will enter into the scheduler and will run this infinite scheduling loop. Like that's why it has because it switches from P1, it switches to this scheduler on CPU 1. On this CPU 2, it switches maybe from P10, P7, P3. So it chooses them out of order, obviously, because they move through this array of CPUs at different speed. So, but when they switch, all of this will be running in parallel, right? And we'll come back to how synchronization and in general, what does it mean to run a multi-CPU system in about a week. But essentially on each CPU, there will be a scheduler, right? If you look at other fields, and we'll come back to it later, there is this task state, a private task state field. And that's the reason for that is that on each CPU will have its own kernel stack, because we have to make sure that, by the way, each of those can do a system call and use its own private kernel stack, obviously. And that's why we have a private global descriptor table, because the global descriptor table has to point to this private TS field, right? So roughly speaking, and this is the proc field of the CPU pointer, of the CPU data structure, is the pointer to the currently running process of this specific CPU, right? We'll get back to synchronization and everything, but at a high level, this is how it works. So on each CPU, x86 enters the scheduler function, and it runs an infinite loop trying to schedule CPUs for running. And this is pretty much how like real, like full-featured operating systems work as well. Make sense? Any other questions? Any questions about it? And so essentially, I'm showing here again this is the kernel stack on one of these CPUs. At some point, there was a return address into main, will be a return address into MP main, but really we will never exit much. We will just get back to this scheduler function, which runs this infinite loop, right? So when we're switching, what we're doing is we're switching from the process into a scheduler, or back for the very first time. When we switch for the very first time, we switch from the scheduler to the process, like it specifically was, remember, user init process with this, which we created, we put it in a table of processes. And when by the time we finish booting, we just say, okay, let's switch into this process. And this is how everything starts running, right? And like essentially, these are the data structures. When we switch for the first time, the from field points to the scheduler field, which is part of the CPU data structure, and the context field points to the context of the very first process. And we essentially this process we essentially created ourselves as part of this user init routine, right? Which we discussed when we were talking about exec. We talked about how the very first process was created. So this is the context of the very first process. It's also kind of like relevant to the homework which you guys are doing, because you say, look, I need to create a context there, and this is the context which we'll be using. Like when you create a new, like when you do a create proc system call, which I'm asking to build in the homework, you will need to make sure that you will correctly initialize those context fields, because despite the fact that the context, the process never ran, it's a brand new process. The very first time we switch into this process, right, we still have to pass a pointer to the correctly initialized context on the stack. Answer a question here. So during the entire context switch process, we switch from old context to scheduler context to the new context. So during the entire context switch process, we switch from the old context to scheduler context to new context. Correct. What, like conceptually, what you're asking probably is the following. In order to switch from process P1 to P2, like in practice, what happens underneath is that you're switching from P1 into the scheduler, and scheduler switches to P2. That's correct. Yeah, in x86, it's kind of like underneath, there will be two context switches, which is a little unusual, right? But this is how they build it. And that's okay. Like, as I said, a normal operating system will probably skip this context switch just because it's expensive, and it will switch from P1 to P2 directly. Any other questions? So, like, again, back to the homework. So I was talking about that if you have to initialize the context correctly, right? And luckily, it's kind of done for you when you allocate a new process in x86 with this function, which is alloc proc function, right? They already kind of like take care of it. So what they do is that they essentially make sure that the context of the process is initialized correctly. So essentially, and the goal for every new process, right? Because it was never forced into the kernel with the timer interrupt or with some other system call, because it's brand new. we have to make sure that the kernel stack of the process, this trap frame and the context, which will be sitting on top of trap frame, is initialized in such a manner that at some point we just can exit into the user level, right? And make sure that we start running the main function of a process, right? Because that's how we start running a process, right? And what happens here is they essentially doing this. They say, okay, they will use a couple of helping functions. So there will be one fork rat and there will be one trap rat. And those functions essentially like implement the logic of exiting into the user level. It's not very hard, so let's quickly take a look. If we have it here, no, probably I don't. But essentially, let me like those slides just repeat the same logic, like from a process into the scheduler, back to a process, back to a scheduler, stuff like that. But what I wanted to get to is the slide which essentially explains how we exiting back to the user level, right? So at some point, like every process which was forced into the kernel with a timer interrupt will have a kernel stack which looks something like this, right? So it may not exactly look like the last functions like yield, like the pass through the kernel can be slightly different. However, the saved registers, which are saved by the interrupt, those error codes and an interrupt vector will be here. All registers will be saved here on a stack. This will be called trap frame. Then at the very top of this stack, there will be something what is called a context, right? And so essentially, if we ever switch back to this process, we will continue exiting through this, like through the return addresses, right? So essentially, we'll get back to a place in yield, you'll get back to a place in trap, trap returns to all trap restores all the registers at the very last moment does the IRAD function, which uses these 5 registers and specifically sets this one to be a user level instruction pointer and this one to be a user level stack, right? Because if interrupt was preempting a user level context, because of course it could also preempt a kernel context, but then you simply exit back into the kernel, right? Because remember in x86, when you do a syscall, you don't really disable the interrupt. So you enter the kernel, you start running in the kernel, but you can be preempted with the timer interrupt in a kernel as well. And then essentially you will return at exactly the same point and continue executing the same system call when, if you even like context switch here, right? And essentially in the end of it, you will get back to the user level, continue running user process because IRAD will force you back back into the user level. Let me take a question from the chat. So when we context switch to a user process, we're really context switching to yield, which goes to trap, which goes to all traps, which completes the switch to the new process. No, it exits back into the old process, right? Because look how it works. Go back here. Like go back quite a bit back here. So for example, I just wanted to like start over. Maybe this idea is not obvious, but imagine, like I wanted to get here. Imagine you were running in user level, right? So your instruction pointer was pointing here, user level text section. At some point, the timer interrupt forces this, preempts this process, right? So essentially forces it to start executing vector 32, handler for the timer. The logic of this handler saves everything on a kernel stack. So the first five registers are saved by the hardware, right? Then we keep saving and saving and saving until we get to a fully packed stack, essentially, which has everything, captures everything what was happening up until we enter the switch function, right? So the stack will look something like this. So here we got preempted with a timer interrupt, but this is the kernel stack of this process P1, right? And like logically, we were running through the kernel, like vector 32, then all traps, then trap, then yield, then scat, and we call switch. And the switch function like will finish saving the state of the process by pushing the context on very top of the stack. But essentially, in the process data structure, so if you have like a list of processes, right, which contain process data structures, you will have a pointer to the context. So essentially, this is like a magnified view of this field, right? So on this pointer, context will be pointing to the very top of this stack, right? And this is how we remember the state of the process we context switch from, right? And so like imagine this process P1 sits in this like process array for quite a bit of time. I don't know, we execute all other processes in this array. And at some point, like, tens of thousands of cycles later, or tens of millions of cycles later, we come back and we want to context switch back to this process P1, right? Since we pass this pointer to the context to the switch function, and it's instead of calling a switch saying that we're switching from a process into the scheduler, we will call it something like switch from a scheduler into this P context, right? This P context will be pointing to this stack, right? Which means that, okay, we're switching from a scheduler to this process P1, which we saved like this before, right? And essentially we will start execute, we will restore the stack and the stack of this process to point to this location. We will return to this return value, which will return to the scat function. The scat function will return to the yield function, because this is what called the scat 10 million cycles prior. Then we will return to trap, and then we will return to all traps. And inside the all traps, we will restore all the user registers, and we'll do the IRAD to essentially restore the user level stack and a kernel and a user level instruction pointer. And these two will get us back. I will scroll back to this one. Oops, sorry, to this instruction pointer right here. Does it make sense? So it's not like you can say that we're completing a context switch, but really it's not a completing a switch to a new process. We just returns to the old process. It restores the state of the old process. Does it make sense?
Yeah, thank you. That sums it up pretty nicely.
No, and I get it. So it's a little unusual, but okay. But at this point, any other questions? So we kind of been back and forth on the context switch for a while, and I hope it's at least somewhat clear at this point, because probably explain it like 5 times. And get it. It's totally like it can be intimidating, but you should be okay. Any other questions? I also wanted to make the following comment, which like despite the fact, I will just use this slide as a white space. Despite the fact that we started from a timer interrupt and did all this kind of like OS-like things, roughly speaking, nothing prevents you to build a similar yield function at user level. Imagine you just want to build some kind of asynchronous runtime, and you say, look, I have a notion of processes at user level. Those typically in the literature, those processes are called user level threads, right? So because it's still like your main function or your language runtime executes the same, like for the operating system, it looks like one process, but you can implement multiple threads of execution. And you can, roughly speaking, you can say, look, I will implement a yield function at user level. You don't have to exit into the kernel, because yield, then you say, I will switch, like just implement the switch function. Switch is not magical. It says, okay, look, I have some current stack of execution. I will, like, maybe I have a global field which says a current process, which is currently executing, right? This current process will have a context field, push everything on this stack, update this context field, and switch, enter, for example, some kind of a scheduling function. And if you have other stacks of execution, which implement other logical or green threads at user level, you can very well, you don't have to exit into the kernel. So you can have thread 1, thread 2, how many threads you want at user level, and you can run them and context switch between them, right? So nothing really, despite the fact that I keep explaining context switch as a part of the kernel, it also can be part of the user level, right? And you can do all these tricks. And this is what specifically different language runtimes are doing. So something like async runtime in Rust, or if it exists in C++ as well, it does something similar underneath. So this kind of flavor of a context switch, but without exiting into the kernel, because exit into the kernel is expensive, and also they want to implement their own scheduling logic. Like if they have a list of threads to run, maybe instead of implementing round robin, they somehow will maintain, sort them as a tree and keep track of which thread was running the most and stuff like that, right? That's my kind of like a finalish comment about the context switch, that it doesn't really have to be in a kernel. So if someone asks you to build one, think of this switch function, think of a Collie saved registers and the stack, and that's it. That's essentially what you need to remember, and then you will be able to build it. Any questions about this? Okay, so now we kind of my slide deck, at some point iterates back and forth. And this essentially, remember this last question, which I was answering, how we go back to the user process. There's, I have a group of slides which do that. So here we again switching from the scheduler to the context of the process. Everything is saved on the stack. We start returning on this stack. We will eventually get back to the user level and get back to where we were before the interrupt started, right? And that's it. So we know how to switch from one process to another. And just to again sum it up, remember my wonderful kind of part which I keep mentioning over and over. We view these operating systems. We typically see them through graphical user interfaces, right? So a bunch of windows which essentially somehow laid out one on top of another, right? We see them on the screen. What happens underneath is the following. So each of these windows, sometimes a process can implement multiple windows. I'm not a big expert on Windows systems, but let's imagine each window is a different process, including this wonderful taskbar, kind of like P5. What happens is that operating system essentially starts running P1. At some point, a timer interrupt forces the P1 into the kernel. The kernel runs the scheduler, switches back to, let's say, I don't know, let's run P3 for a second. P3 again, maybe voluntarily yields because it waits for the, instead of a timer interrupt, maybe it's a yield because it waits for the user input. And I wanted to write a mouse here. I don't know, it doesn't look like a mouse anymore. That's a mouse. And goes back into the scheduler. Scheduler again, for the simplicity of the argument, let's just imagine the system has one CPU, right? So nothing really, no multi-processing, just one CPU, just very fast context switches back to something like P2. And essentially, if each of these processes gets a chance to run, including maybe there is some kind of a global P6 process, which is, call it compositor, which implements the logic of this Windows system. So when P1 runs for a little bit, somewhere in its own memory, it creates this window. It's just maybe draws pixels, which represents its state on the screen. So this window for P1, P3 ran and like updated its own window a little bit. This is for P3, like some kind of a pixels thingy. Like, I don't know, let's draw it, making sure that it kind of looks similar. And P1 has those. Great. Then P2 again, also updated some kind of a, you usually do that through like graphical user libraries, right? Which draw some lines or widgets on the screen, right? When compositor gets a chance to run, like let's run a compositor here at some point after switching to it, compositor just says, okay, I will like essentially, typically this memory is shared across between the individual graphical processes, like GUI processes and the compositor. Compositor says, okay, I get it. I have that. I understand that P1 sits on top of P2, and I know the coordinates of those like X and Y coordinates and a Z coordinate. I know X and Y coordinates in a window system of P3 as well. Then compositor just says, okay, I get it. I will assemble those individual windows of P1, P3, P4 in this kind of like way, P1, P2, P4, and P3. And at this point, like this memory is ready to go to the graphical adapter. At this point, P6 like calls into the kernel and essentially says, okay, guys, and kernel implements some kind of a device driver, which sends those pixels like over, let's say, a VGA cable to a real screen. And just, this is how you see this image of everything what's running, right? But essentially, the key point here, and I mean, it sounds, at this point, I agree, it sounds borderline trivial, but the main point is that like they all took a chance and they ran, and the system was context switching between them. They all updated their own windows and some as regions of memory somewhere. Then a compositor program, which is also typically just a regular process, copied those and like it composed them together, one on top of another, keeping track of all these coordinates, and then pushed into the kernel, which implements a device driver, which we can cover later. Like it's kind of similar. You already in your homework, remember, we were printing hello world. And we were just like sending ASCII characters. So each byte is representing a letter. Because you ask a question, okay, I sent a number, who draws this H? It's implemented as a part of the VGA adapter. And of course, like real GPUs are way more complicated and everything, but at a high level, you just send information about those pixels to a real physical graphic card, which can take them in different formats. And then also it runs a tiny firmware, which essentially does some additional processing and stuff like that. I don't know, maybe does some shading or whatnot, and eventually puts them on a screen as a collection of pixels, right? But that's kind of the main idea of everything, is that, you know, we learn how we create individual processes. We learn how to create address spaces. We learn how to count, how to switch between them. And essentially at this point, we can kind of understand what's going on when the operating system is running. Let me stop here for questions. All good? Okay, then we're done with the context switch, and we will start our next set of lectures on the file systems. So let me quickly stop sharing the slide deck, switch to a different one. And the new one will finally explain us how the file system is implemented. Where's my slide deck? Here. And where is it? Let me start, share it. Okay, so somehow started playing again the same lecture. That's bad. Let me open file system. Okay, here we are. Slideshow. Share it again. Okay, file systems. we'll spend a couple of weeks, maybe at least a week. I think it will take us this lecture and the entire next week to cover file systems. But at a high level, our goal is to like understand this last, not last, but one of the last big pieces of the operating system, which we haven't discussed yet, and essentially the idea how we can expose like raw disk space as a collection of folders and human readable file names and enforce certain properties like crash consistency and other things on top of this like hierarchy of levels which implement the logic of a file system. So if I ask you a question, so why do we need a file system? What's the purpose? Anyone?
Probably just organization of all your code and stuff.
At a high level, you say, look, we as humans, we like to think in terms of like, I don't know, root folder, kind of like bin, lib, I don't know, cool, Anton, stuff like that, right? And here I have something like foobar files, empty. That's correct because I've been like what's underneath is the following. We have a disk. Think of disk as roughly physical memory, right? You can think of it, right? Despite the fact that the memory of a disk is typically accessible in the units of blocks, like probably 512 or something. But it's just like starting from block 0, 1, 2, 3, and everything, right? And you can say, look, sure, it's kind of like if you want to store information, you obviously need to keep track of which of these blocks are allocated and which of them are free, right? You say, look, I started saving a file foobar MD. Maybe I put it in this block number 3, and maybe it even fits in block number 3. But then say I keep adding data and suddenly I need to essentially 2 blocks to save this file. Maybe the adjacent block is already used, so I have to skip it and pick another one. So for this, you need some kind of an allocator. It's somewhat similar to the physical memory allocator, which we built in x86, right? Because it really needs to keep track of which blocks are available. And you say, look, but also you need to translate because you say, look, logically, I want my file to look at 2 consecutive blocks, maybe starting at address 0, then going to address 512, and so on, right? And when you say, I want to read a file, and I read a block which is, let's say, on the boundary between these 2 blocks, 511, and I want to read, let's say, like 8 bytes or something, right? So and I have a file descriptor here. This 511 falls right at the end of the first block, has to go into the second block. So this read function should somehow internally keep track of where those blocks are located on the disk, right? So it's like this one block is here, the second block is somewhere here. Logically, it looks like it's a continuous file, but in practice, it's all over the place, somewhat similar to how virtual memory is mapped on top of physical memory, right? So every time we allocate a new physical page, we go to the allocator, right? That's fine. So that's one role of the file system to make sure that we kind of keep track of where the data is actually saved, right? We also say, look, I don't want to remember that that the file starts in block number 3 or something like that. I want to give it a human readable name like a foobar. And for that, you need enough metadata, some kind of a library, some kind of a table which keeps track that foobar MD, this specific name starts at file at a block number 3, right? So it has to resolve from these string names into somehow like blocks on disk and maybe some intermediate levels as well. Those intermediate levels are called inodes, right? So we'll talk about them, right? But just to give you a hint of what's going on. Then, of course, we want to be able to maintain the hierarchy of those folders and directories, right? Meaning that it's not just a flat space, because you can say, look, maybe my file system doesn't support hierarchy, it just supports just the names, right? It's a viable solution. So I was trying to tell you that I've been on projects where we were building primitive file systems because we didn't have space. The file space was so limited that we couldn't. We chose not to have the hierarchy. Maybe it wasn't a smart choice, honestly, but like essentially we just were saying, okay, we just have flat files and that's it. Like one, just this root folder and then like files like A, B, and C. And the project was about like storing those cryptic keys. So like really there was no space for that. But really, as humans, we like the hierarchy, and it helps us to organize things in this manner. And it doesn't have to be hierarchy always, because on Facebook, for example, we don't care about the hierarchy of people on Facebook, right? Or maybe some people do, but most not. We just say, okay, we want to be kind of like content addressable. We say hashtag whatever cs50 what is it, 5464, is that the class number? I don't remember myself. 60. And we say, look, it's all the files related to this hashtag. So instead of a hierarchical data structure, we implement some kind of a more complicated database in which we say, look, we use this as a key, and we just search everything what is related to that key. And that also can be done in a file system. So the file system doesn't strictly have to be hierarchical. That's one way to resolve from names to from names to intermediate representation of files, which we call inodes, right? But roughly speaking, that doesn't have to be this way. And finally, a couple of other things which are kind of interesting, which are like, okay, maybe stop and give you a chance. So, okay, I explained this part of the file system. What else do you think file system needs to be doing as well?
When you create a new file, it needs to allocate a block of memory for that name.
Yeah, so it has to like keep track of new names, like boss here, right? But maybe I'll give you a hint related to performance. Do we need to do something in a file system which may optimize performance of accesses?
Have indexes of or a table of file, or I guess.
No, you're right. So when there will be some kind of a data structure which will be kind of similar to a radix tree, of a similar radix tree of a page table, which allows us to resolve from logical addresses within a file to specific physical blocks and disk. So that's there. But I was asking more generally. In general, disks are relatively slow. So do you see an opportunity for optimizing the access to files in the face of slowish disks?
Maybe we could solve it like most problems and introduce another table that keeps track of recent files.
Correct. So it's called a cache. So essentially, we never talked about it because we haven't seen a problem like that in this class yet. But really, the access to the disk, to this essentially physical disk, is so slow, right? I mean, non-volatile PCIe attached SSDs, NVMe drives are reasonably fast. They are like in tens of microseconds. So which means like roughly 20,000 cycles, right? That's not bad, but spinning disk like real SATA disks, the accesses are in the order of not microseconds, but milliseconds, which means it's like 2 million cycles to get the block from disk, right? And if you're saying, look, when I do a read, maybe if it's a popular file, maybe it's this table itself, which is also saved on disk, maybe it makes sense to implement some kind of a cache in memory. Just which will be caching frequently accessed blocks. So essentially, the first time you access the block, you bring it in memory and you keep it around for a while. It's kind of similar to a cache of a CPU, right? So L1, L2, L3, and then slow memory. So it's similar here. We bring blocks from disk into memory and keep them around, maybe in some least recently used order or something like that, to know when we to have some policy for eviction, right? But really, like, having this in memory allows us to like spend a millisecond once and then maybe amortize accesses by saying that, you know, there is some spatial and temporal locality. We can also implement a prefetch and maybe read adjacent blocks or something like that. And this is also what the file systems are doing. So in light of slow disks, it was a like life-saving mechanism to improve performance, right? So it's similar between the caches and memory, but it's all implemented. If caches are implemented by the CPU themselves in the logic of this gates and everything, we implement it in software. And the moment we have a cache, we also need to make sure that if we lose power, meaning like there is a power event and machine just immediately stops running, if we did some writes into those caches, and maybe we flash some of those blocks back to disk, that we flash them in such a manner that we can come back and read this file system again. And it will become clear, but imagine like if there are some pointers between those data structures, because like you say, look, I allocated a new thing and this new thing is no longer free. And it's effectively like a pointer from an allocator to a block. You have to make sure that you flash those writes in some kind of a manner that they are not out of order and it's some consistent state. So one has to implement this consistency. And we'll take a look at how it's done. But essentially, the idea is that the file system has to be resilient to power loss because it's quite frequent, right? Like you maybe less frequent in the last decade, but it used to be. The idea of losing your data on the file system was around when I was a student. Questions: efficiency, consistency, and redundancy. Redundancy is there too. Well, like essentially, we don't have it, but in this class, but essentially the redundancy comes when you say that the disk itself can bit flip, essentially just losing individual bits just because, you know, it's a mechanical error and you use like magnetic memory and it just lost a bit or something like that, then you might have to run some kind of error correction scheme to make sure that first you detect an error, and second, if you have enough redundancy, you can recover from an error. And that's called like RAID arrays, where you like, instead of writing one block, you write 3 blocks and then computer checksum on top of them, right? But okay, so if we have an overview of what needs to be done, let's kind of like dive into it and understand what is actually, how is it built, right? So roughly speaking, like again, our old goals, we will be sharing one single disk. I didn't mention sharing across multiple users, multiple processes, and multiple maybe principals, like users which sign into the system, right? We will implement the idea of persistent storage, meaning that, of course, we save data on disk, we reboot the machine, we lose power, we switch it off, we come back, data is available after reboot. Also, it's crash consistent, meaning that if we lose power unexpectedly, then when we come back, we can read the file system and in some consistent state. We don't have like dangling pointers, and we don't lose, everything is kind of like garbage collected, or we don't lose blocks which we believe are allocated, but there are no pointers anywhere in a file system to those blocks. Conceptually, a file system is represented as a collection of data structures on both disk and in memory, right? So obviously, in order to read the file system, you have to save everything on disk, meaning if you want to read it after you power off the machine, nothing stays in memory. However, for performance reasons, right? So you don't always just read from disk. You first read certain metadata in memory to make sure that you Again, you optimize everything, and you don't have to go to disk on every memory, on every access to the file system for both metadata and for like frequently accessed blocks of files, right? So that's why file system is kind of exist in two places, on disk and in memory, and you have to make sure that they are kind of in sync and never inconsistent, right? At a logical level, we represent files as a tree of files and directories, so it's kind of convenient for humans. We keep track of where the files are on disks, right? So we already talked about it. We keep track of which areas of disk are free and allocated as well. We provide this crash recovery, which I mentioned. So essentially, if there is a power loss, then we will reboot and make sure that we will recover into the state which makes sense. It's kind of like, it's hard to understand immediately, but I'll provide more concrete examples and you will understand what it means, how you can end up in an inconsistent state. And finally, like we do this optimizations to make sure that we try to reuse frequently accessed blocks, and we read them once into memory from disk, and then read them multiple times from a cache which we maintain in memory. So a file system is implemented as a collection of layers, right? At the very at the very top of this is the interface of system calls. At the very bottom is an interface which interfaces with individual blocks of the disk. At this point, there are no abstractions of file or anything. It's just blocks. And this layer implements buffer cache. So it's essentially, it first of all, like caches frequently accessed blocks from disk, and also tries to synchronize or implement synchronization between multiple processes, meaning that, you know, if multiple processes in the system try to write into the same file, the buffer cache will enforce synchronization discipline, making sure that only one process can write. On top of that, there will be a layer of journaling or logging. This layer will implement consistency, meaning that it will group writes into groups of atomic transactions, and meaning that if we lose power in between a series of writes, we will be able to roll back to the state of the file system like none of these writes happened at all. And if we complete all the writes, we will update the file system in a single atomic transaction saying, okay, commit those writes. And at this point, if you reboot, you will come back and you will see those writes as done in the file system. On top of this layer, we implement a level of inodes, and essentially inodes represent unnamed files. So it's an inodes map from imagine a file, but without a name, and just has a number. Inodes are identified by numbers. But then it's kind of like a page, like radix tree, which is page table-like data structure, which maps addresses within a file into individual blocks on disk, right? On top of those inodes, we give them names, and this essentially we implement directories, file names, which humans can read. And on top of that, we have a layer of this hierarchical path lookup. We've seen it before. Remember when we were doing exec system call, I was using a function name I. It takes a name in the form of a path, and the logic of this name I functions, it will be parsing this name, essentially moving from a user directory inside the bin directory, inside the bin, it will find a sh file, and from this sh file, it will return an inode. Essentially, it goes from a name to an inode, and it returns an inode pointer. And finally, on top of this, since inodes can be opened by multiple processes at a time, we'll have an interface of file descriptors, which are used by the system calls, right? Essentially, we open a path, it gives us a file descriptor, multiple processes can open the same file, stuff like that, right? So now, like, if I get it, so it's a little hard to like immediately understand what these layers are doing. We will now study them one by one. We'll start from the bottom, from the buffer cache, and then we'll go up, looking at implementation of each of those layers. Any questions about this hierarchy? All good? with the overview. Okay, let's go into those levels. So first, layout of the file system on disk, right? Every time you kind of like, you see a new disk, the kernel, the operating system kernel sees a new disk, and it assumes that the disk will have a file system. You have to start somewhere. It's kind of like an ELF header file, right? The header file, the header data structure of the ELF file, right? In a file system, this block is called a super block. Essentially, the file system, and it's a convention, says, okay, the very zero block is a boot block. Our boot code, remember this 512 bytes, which we saved in the 7C00, it's not us, we didn't save it, but the BIOS essentially read this from the boot block 0 of the disk into the file system from the block 0 into the address 7C00. So this block number 0 contains this logic of the boot block. So essentially, it's this assembly code which we compiled. On top of that, the operating system, when it opens the file system, it reads the super block. The super block is the top level metadata about the file system. It's located in block number 1 by convention, and the information what it contains is the following. So it essentially, it describes the sizes and locations of individual metadata areas on disk. So specifically, we'll see a couple of those, right? And we will have this journaling area or the log, which will allow us to implement a journaling file system. And so the super block says, okay, I have n blocks in this journaling area. On top of it, there will be some number of blocks which keep track of individual inodes, right? So its inodes represent unnamed files, and each of these inodes is like a data structure. We'll take a look at what's inside, but essentially there is some number of those. And this inodes area essentially occupies some number of disk blocks, and this is contained in this super area. On top of that, just to be concrete, each inode, and just to give you an overview, because we'll come back to it and cover it at a level of, the different level of details. So essentially what each inode is representing is the following. So this inode on disk is called the inode. This one element of this array, which I keep drawing here, this is one element, contains some metadata about the file. It has a type. It can be a directory or a regular file. It has a major and a minor number. Don't worry about it. This right now, it has a number of times this inode is referenced from different part of the file system. When this n-link number drops to 0, inode becomes free and the operating system deallocates it. It maintains the size of the inode, but the most important part is the hierarchical metadata table, which maps addresses of individual logical block of a file into blocks on disk. So essentially block number 0, when you try to read a block number 0 from a file, there will be a number 55 here, which says, okay, the logical block 0 of a file is located at block 55 on disk, stuff like that. And essentially it can be organized as a tree as well. And so this way you can have a file of a specific max size, but essentially every time you try to read block number, let's say 17, you say, look, I have 12 direct blocks. I keep track of 12 blocks here directly in the inode data structure. If it's indirect, then I go into this table. So I subtract 17 minus 12, get 5. So I get into the position number 5, and get the block number here. We'll cover it later, but this is the inode, right? And this is how you represent the file, unnamed file on disk, right? And so you have an area which keeps track of individual inodes in a file system. On top of the inode, you will have an area which keep tracks. It's a bitmap. So if in x86 we kept track of allocated and unallocated physical pages as linked list, which was making sense because we were avoiding ON problem. x86 file system doesn't do that. They just keep track of allocated and unallocated blocks in the data area in form of a bitmap. So roughly speaking, 0 means unallocated, 1 means allocated, and if you want to allocate a new block, you have to scan the entire bitmap area, making sure that, guys, we will scan through and we will allocate memory. We'll until we encounter an unallocated block, and then this data area is allocated for a file. And finally, at the very top of it is a data area. So actually, this is where the data from files is kept. So essentially, if you look at the inodes, those blocks are allocated from the data area, right? So let's quickly do a poll. I know we only have 1 minute. I apologize, but we made it to this point, and let's quickly take the attendance. So you see it on my screen. The question which I'm asking is very simple. What is contained in the bitmap area in this one? Just real quick, wait for everyone to answer. So can anyone tell us the right answer for everyone who is on Zoom?
You went pretty quick on this part, but I said unused blocks in the data area.
And I believe it's correct because some people are unsure about it. So bitmap, some people say bitmap keeps track of unused inodes. That's incorrect. And some people say bitmap keeps tracks of unused files in the file system. So really bitmap keeps track of unused data blocks. So essentially, 1 bit in the bitmap area corresponds to 1 block in the data area. And for inodes, they will just implement the same algorithm, but they will be scanning through the inode array looking for unallocated inode. It's also pretty slow. It's ON. And bitmap gets even slower because the bitmap is way larger, because the file system can be relatively large depending on how you configure it, right? But scanning through the bitmap area becomes slow. It's ON. And real file systems obviously don't do this, but x86 makes the simplification. But essentially, it's the bitmap tracks unallocated data blocks in the data area. Okay, so then I think we should stop here and we'll come back in person on Tuesday. I will continue on the file systems. Don't forget to work on your homework, and I will have my office hours on Zoom today in about half an hour. So if you have any questions, go for it, ask me. Otherwise, have a good weekend, and I will see you next week. Just stop this.